What happens when something from the farthest depths of the universe decides to visit us, right now, at this very moment in human history? Stay with me until the end, because what is happening in our night sky could forever change the way we understand our place in the cosmos. This week, while you go about your daily activities, an ancient traveler is crossing our cosmic neighborhood, and NASA has just confirmed that its closest approach to Earth will occur this 19th of December.
My friends, Felipe Suarez here, and let me tell you something from the heart. How many times in our lives do we have the opportunity to witness something that comes literally from another star system? Think about it for a moment. This comet, this piece of ancestral ice and rock, was not born here. It did not form in our solar system. It traveled distances that the human mind can barely conceive. And you know what is most extraordinary? That you and I are alive to see it pass by. Does it not seem to you that the universe is giving us something special?
Comet 3, I/Atlas, as astronomers have officially named it, represents only the third confirmed interstellar object to cross our solar system in the entire history of modern astronomical observation. It was discovered during the summer of this year, specifically in the month of July, by the Atlas telescope located in Chile, while its operators were scanning the sky in search of asteroids potentially dangerous to our planet. No one expected to find a visitor from so far away. NASA continues to point its most powerful space telescopes toward this wandering ball of ice, whose size is estimated between 440 meters and 5.6 kilometers in diameter. It is an enormous variation in the estimates, which indicates how much we still do not know about this mysterious object crossing our cosmic neighborhood with a speed that defies our everyday understanding of movement. This Friday, this interstellar visitor will pass at a distance of approximately 269 million kilometers from our planet. It may seem like an immense distance, and it certainly is in human terms, but on astronomical scales, it represents the closest point this object will reach relative to Earth during its entire journey through the solar system. It is, literally, its farewell before beginning the long journey back toward interstellar space. For those who have telescopes in their homes, this is the ideal time to try to observe it. The comet is gradually fading as it moves away from the sun, losing the brightness that made it visible. So the coming nights represent the last realistic opportunity for amateur astronomers to catch a glimpse of this messenger from distant stars. But the story of 3I Atlas does not end with its close pass to Earth. In March of next year, the comet will approach Jupiter considerably, passing just 53 million kilometers from the gas giant. This proximity to the most massive planet in our solar system represents a crucial moment for scientists who hope to observe how the tremendous Jovian gravity affects the behavior of the visitor. Paul Chodas, director of NASA's Center for Near-Earth Object Studies, has explained that the comet will not reach interstellar space proper until the mid-2030s. Once it crosses that invisible border, it will never return to our solar system. It will be gone forever, taking with it all the secrets we have not managed to decipher during its brief visit. Scientists believe that this intruding comet, as some have affectionately called it, may have originated in a star system considerably older than ours. This possibility makes it an absolutely fascinating object of study, because it could contain information about the conditions that existed in regions of the cosmos when our own sun had not even been born yet. Interstellar comets like 3I Atlas originate in star systems located in other parts of our galaxy, the Milky Way. Unlike local comets, such as the famous Halley, which come from the frozen regions at the edges of our own solar system, these visitors have traveled distances that defy our capacity for imagination. They have crossed the void between stars, that seemingly empty but mystery-filled space, for millions or perhaps billions of years. The first confirmed interstellar visitor was discovered in the year 2017 by a telescope located in Hawaii. That object, named Oumuamua, which in Hawaiian language means approximately messenger from afar arriving first, caused a commotion in the scientific community that still resonates to this day. Its elongated shape, similar to a cosmic cigar, and its anomalous behavior generated debates that continue without being completely resolved. 2 years later, in 2019, an amateur astronomer in Crimea detected the second known interstellar comet. And now, with 3I Atlas, we have the third confirmation that these visitors from other worlds cross our solar system more frequently than we imagined just a decade ago.
Do you realize what this means, dear listeners? In less than 10 years, we have gone from having no confirmed interstellar objects to having 3. How many more may have passed without us detecting them? How many crossed our sky while our ancestors looked upward without the instruments to see them? Technology is finally allowing us to witness something that was always there, waiting to be discovered. Does it not give you goosebumps to think about that?
The most recent images of 3I Atlas, captured by teams of astronomers working in different parts of the world, including facilities in Mexico, have revealed characteristics that have the scientific community in a state of genuine fascination. This comet is not an ordinary visitor in any sense of the word. Its behavior from the very moment of its detection has shown peculiarities that defy some of our expectations about how these objects should behave. The trajectory of the comet has been the subject of meticulous analysis by specialists in orbital mechanics. Every measurement, every calculation, every computational model seeks to predict with the greatest possible precision where this fragment of ancient matter is heading and how it will interact with the bodies of our solar system during its journey. To understand the importance of the anticipated encounter with Jupiter, it is necessary to understand a fundamental concept of planetary astronomy known as the Hill radius. Imagine an invisible zone that surrounds any massive planet, a subtle border where the gravity of that world begins to exert a dominant influence over the gravitational attraction of the Sun. It is like its own territory, a gravitational kingdom that defines the extent of each planet's influence. Jupiter, being the undisputed giant of our system, possesses a Hill radius that extends for more than 53 million kilometers in all directions from its center. It is a sphere of influence so vast that it could contain Earth and its lunar orbit several times without any problem. And 3I Atlas, according to current projections, will pass grazing that gravitational limit during its March flyby. The precision with which the comet will approach this invisible border has caught the attention of numerous researchers. In the world of celestial mechanics, where distances are measured in millions of kilometers and trajectories are calculated considering the gravitational influence of multiple bodies simultaneously, finding an object that follows such a specific route inevitably generates questions about the factors that determine that path. Comets, unlike asteroids composed primarily of rock and metal, are largely made up of ices of various chemical compositions mixed with dust and complex organic compounds. When these objects approach the Sun, solar radiation heats their surface and causes those ices to sublimate, passing directly from the solid state to the gaseous without transitioning through the liquid phase. This sublimation process generates jets of gas that escape from the cometary nucleus with considerable force. Those jets act like small propulsion engines, pushing the comet in directions that can subtly modify its original trajectory. It is a well-documented phenomenon, studied for decades, which explains why comet orbits often show small deviations from predictions based solely on gravitational forces. Outgassing, as this process is technically called, typically produces pushes that we could describe as chaotic, or at least difficult to predict with total accuracy. The irregular distribution of ices on the surface of the nucleus, the rotation of the comet on its own axis, the variations in the intensity of solar radiation, according to distance, all these factors contribute to generating emission patterns that are complex to model mathematically. However, scientists have developed sophisticated techniques to incorporate these effects into their orbital calculations, allowing reasonably precise predictions about the future behavior of known comets. What makes 3I Atlas especially interesting is that it comes from an environment completely different from that of any local comet, which means its chemical composition could include ices and compounds that we have never had the opportunity to study directly.
Friends, allow me to ask you a question. Have you ever thought about what it means for an object to come from another star system? We are not talking about something formed in the outskirts of our own cosmic neighborhood. We are talking about matter that condensed around a completely different star, perhaps a cold red dwarf or a blazing blue giant. What chemical secrets might it hold in its frozen interior? What story would it tell us if we could decipher its molecular composition?
Telescopic observations of 3I Atlas have revealed that the comet develops the characteristic tails that distinguish these objects when they approach the Sun. Solar radiation and the stellar wind, that constant flow of charged particles emanating from our star, push the dust and gas released by the nucleus, creating those luminous trails that have fascinated humanity since time immemorial. Our ancestors contemplated these celestial apparitions with a mixture of awe and fear. They interpreted them as omens, as divine messages written in the firmament, as warnings of transcendental changes to come. Today, we understand that they are perfectly natural physical phenomena, the result of the interaction between cometary material and energy coming from the Sun. But 3I Atlas presents a characteristic that very few comets show and that has generated particular interest among specialists. An anti-tail, that is, a tail that seems to point toward the Sun instead of away from it. This phenomenon, although documented in some previous comets, is relatively rare in astronomical observations. The anti-tail is produced when relatively heavy particles, released by the cometary nucleus, remain suspended along the object's orbit. Depending on the angle from which we observe, these particles can create the optical illusion of a tail that defies apparent logic, pointing in the opposite direction to what is expected. It is fundamentally a perspective effect, a consequence of orbital geometry and our relative position as observers. However, the specific characteristics of the anti-tail of 3I Atlas have drawn attention for their particularly defined structure. The physical models we use to describe the behavior of cometary dust predict certain dispersion patterns over time: solar gravity, the constant pressure of radiation, the small perturbations caused by the presence of the planets. All these factors should contribute to particles gradually spreading in broad and diffuse patterns. The images obtained from various observatories, including facilities located in Mexican territory, show structures in the comet's tails that constantly evolve. They are not static formations, as might be expected from a simple fragment of ice and rock adrift. They change shape, develop new structures, respond in complex ways to the changing conditions of the space environment. Astronomers are documenting these variations with scientific meticulousness, recording every observable change, every fluctuation in brightness, every new structure that emerges from the regions near the nucleus. It is work that requires extreme patience and sustained attention, but that is fundamental to building a complete understanding of this extraordinary visitor. One of the aspects that has generated the most intrigue in the scientific community is the variability of the object's brightness. The light curve, that detailed record of how luminosity changes with the passage of time, shows fluctuations that researchers are carefully analyzing. These variations can provide us with valuable information about the shape of the nucleus, its rotation period, the distribution of active regions on its surface.
Listen well to this, friends. Every fluctuation in the brightness of this comet is like a heartbeat, like a cosmic breath that speaks to us from unimaginable distances. Does it not seem poetic to you that we can read those luminous signals and translate them into knowledge about an object formed billions of years ago around a star that perhaps no longer even exists? Science gives us moments of profound connection with the universe. When was the last time you looked at the night sky and felt that connection?
The study of interstellar comets represents a relatively new frontier in astronomy. Until a few years ago, we had no direct confirmation that these objects crossed our solar system, although astrophysical theories had predicted their existence for decades. Detection technology simply was not advanced enough to identify them among the multitude of objects that populate the night sky. Modern telescopes, equipped with high-sensitivity sensors and computational algorithms specifically designed to detect moving objects, have transformed our ability to scrutinize the cosmos. The Atlas telescope, which discovered 3I Atlas while tracking potentially dangerous asteroids, exemplifies this new era of automated and highly efficient celestial surveillance. These observation systems operate almost continuously, capturing images of the sky night after night, automatically comparing them to identify any luminous point that moves against the stellar background. It is work that would have been impossible for human observers working manually, but that computers perform with an efficiency that just a few decades ago would have seemed like science fiction. The discovery of Oumuamua in 2017 marked a historic milestone in astronomy. It was the first time we could unequivocally confirm the presence of an object born outside our solar system crossing our cosmic neighborhood. The scientific community received the news with a mixture of enthusiasm and perplexity, because the object showed characteristics that no one had anticipated. Its elongated shape, estimated in proportions of approximately 10:1 between its length and its width, was completely unusual for any known asteroid or comet. Natural objects in our solar system tend to be more rounded, shaped by accretion and collision processes that favor more compact forms. Such an elongated object raised immediate questions about its origin and formation. Furthermore, Oumuamua showed an anomalous acceleration as it moved away from the Sun, an additional push that could not be explained solely by gravity and solar radiation pressure. Scientists proposed various explanations, from outgassing of exotic ices that did not produce a visible tail, to the possibility that the object was extremely porous and light, acting almost like a solar sail propelled by starlight. Professor Abraham Loeb of Harvard University, a prominent and also controversial figure in these debates, suggested that the anomalies of Oumuamua were so significant that the scientific community should seriously consider all explanatory possibilities, including hypotheses that would normally be dismissed as too speculative. Loeb did not categorically state that Oumuamua was an alien spacecraft or some type of extraterrestrial technology. What he argued, with the caution proper to a rigorous scientist, was that the observed anomalies were so difficult to satisfactorily explain with known physics that it would be scientifically irresponsible not to keep an open mind regarding all possibilities. This position generated considerable debate within the astronomical community. Some colleagues criticized Loeb for venturing hypotheses they considered premature or sensationalist. Others recognized the value of maintaining a genuinely open attitude toward phenomena that challenge our established expectations. The debate continues to this day, now fueled by the arrival of 3I Atlas and its own peculiarities.
Do you know what I find most fascinating about all this? That a Harvard scientist, someone with hundreds of publications in prestigious journals, is saying we should keep an open mind. He is not stating anything extraordinary with certainty, but he is also not closing doors prematurely. Should we not all adopt that attitude toward the mysteries of the universe? How many times have we dismissed ideas that later turned out to be correct simply because they seemed too strange to us?
The relationship between interstellar visitors and Jupiter represents a pattern that some researchers have begun to notice with growing interest. Oumuamua, the first confirmed visitor, also interacted significantly with the gas giant during its journey through our solar system. It used Jupiter's tremendous gravity to accelerate its exit, gaining additional speed through what specialists call a gravitational assist maneuver. This gravitational assist technique is not something exotic or mysterious. Our own space probes have used it dozens of times with resounding success. The Voyager 1 and Voyager 2 missions, those ambassadors of humanity now navigating through interstellar space, used Jupiter precisely for that purpose more than 4 decades ago. The maneuver allowed them to reach speeds that would have been impossible to achieve solely with the fuel they carried on board. The physical principle is relatively simple to understand. When a spacecraft, or any object, approaches a massive planet from a certain angle, the planet's gravity accelerates it during the approach. If the geometry of the encounter is correctly calculated, the object exits the planetary gravitational field with more speed than it had when entering, having stolen a tiny fraction of the planet's orbital momentum. It is an elegant and extraordinarily efficient energy transfer, which space agencies have systematically exploited to send missions to the edges of the solar system without the need for astronomical amounts of fuel. And now we observe that interstellar visitors seem to follow trajectories that take them close to the ideal planet to perform exactly that type of maneuver. Jupiter is, by an enormous margin, the most massive planet in our solar system. Its gravitational influence extends over tremendous distances, affecting the orbits of countless objects, both local and visitors. From a purely statistical perspective, it would be reasonable to expect that many objects crossing the system would end up interacting with it in one way or another simply due to its gravitational predominance. However, the observed pattern generates questions in some curious minds. 2 interstellar visitors detected to date, 2 trajectories involving significant encounters with Jupiter, 2 sets of characteristics that challenge some conventional expectations. The human mind is naturally inclined to seek patterns, to connect scattered dots, to construct coherent narratives from fragmentary data. Sometimes those perceived patterns turn out to be illusions, simple coincidences magnified by our innate tendency to find order in the apparent chaos of the universe. But other times, those patterns represent the first clues to genuinely significant phenomena, early signals of something we are just beginning to glimpse, and that deserves deep investigation.
My friends, let us think about this together for a moment. If you were an advanced civilization sending exploration probes across the galaxy, would you not use giant planets like Jupiter to adjust trajectories and gain speed? It is exactly what we do with our own spacecraft. Is it a coincidence that these visitors follow similar routes? Probably yes, but the question deserves to be asked. What do you think about it?
The encounter of 3I Atlas with Jupiter, scheduled for March of next year, represents an extraordinary scientific opportunity that astronomers around the world await with palpable anticipation. During that flyby, scientists hope to observe how the comet responds to the intense gravitational influence of the giant planet, and how that interaction could affect its cometary activity. If the object shows significant changes during the encounter, if it develops new structures in its tails, if it experiences unexpected variations in its brightness or behavior, all of that would provide valuable clues about its internal composition and the physical processes that govern it. On the other hand, if the flyby passes without notable incidents, with the comet behaving exactly as standard models predict, that would also communicate important information. Science works that way, advancing with both expected and unexpected results. Every observation, every piece of data collected, every measurement made, contributes to building a more complete picture of reality, regardless of whether it confirms or contradicts our previous hypotheses. It is a process of continuous discovery, a permanent conversation between humanity and the cosmos that surrounds us. NASA's space telescopes continue to monitor the visitor with their most sensitive instruments. From orbits high above Earth's atmosphere, these observatories can capture wavelengths of light that do not reach our planet's surface, providing information complementary to observations made from the ground. The combination of data obtained from multiple platforms allows building a multidimensional portrait of the object. Simultaneously, ground-based observatories distributed across various countries and continents contribute their own contributions to this truly global scientific effort. Facilities in Chile, where the comet was originally discovered, continue their systematic monitoring. Telescopes in Hawaii, the United States, Europe, and other regions add their observational capabilities to the collective project of studying this interstellar messenger. Mexican facilities have demonstrated notable capabilities in this field, contributing high-quality observations that are being incorporated into international analyses. The clarity of the images obtained, the resolution achieved, the ability to document fine details in the cometary structures, all of this represents a significant contribution to the collective knowledge about 3I Atlas. This international collaboration exemplifies the best of contemporary science. There is no single nation or institution that possesses all the answers or all the resources necessary to understand phenomena of this magnitude. The advancement of knowledge requires cooperation, open exchange of data and ideas, willingness to work together toward common goals that transcend political borders and institutional rivalries.
Does it not seem beautiful to you that scientists from all over the world are collaborating to study this visitor from the stars? Mexicans, Chileans, Americans, Europeans, all sharing their observations, their analyses, their discoveries. In a world that sometimes seems so divided, science reminds us that we are a single species, inhabiting a single planet, looking together toward the same infinite sky. When was the last time something made you feel that profound unity with the rest of humanity?
Comet 3. Atlas poses fundamental questions about our place in the universe and about the nature of objects that travel between the stars. If it indeed originated in a star system older than ours, as some scientists suggest, then it could contain materials and compounds that formed under conditions very different from those that existed when our own sun was born approximately 4,600,000,000 years ago. The chemistry that governs the formation of planetary systems depends sensitively on local conditions, the temperature of the progenitor nebula, the relative abundance of different elements, the presence or absence of radiation from nearby stars, cataclysmic events such as supernova explosions that may have enriched the material with heavy elements. Each star system is a unique chemical laboratory, producing mixtures of substances that reflect its particular history. A comet formed in an environment different from ours could contain types of ice that we have never had the opportunity to study directly. Complex organic compounds that do not exist in any local asteroid or comet. Crystalline structures that behave in unexpected ways when heated by the radiation from our star. All that chemical diversity would represent a treasure of information about the conditions that prevail in other regions of the galaxy. Unfortunately, the distances involved make it impossible, with current technology, to send a spacecraft to study 3I Atlas up close or collect samples from its surface. The comet travels at tremendous speeds that our space vehicles cannot match, and the preparation time necessary for such a mission far exceeds the available window of opportunity. Some dreamers in the scientific community have speculated about future technologies that could allow the direct study of interstellar visitors. Concepts such as ultralight solar sails propelled by powerful lasers, capable of reaching significantly higher speeds than conventional probes, could someday make intercepting these fleeting objects achievable. But that day remains firmly in the future, beyond the reach of our present capabilities. Meanwhile, we depend entirely on remote telescopic observations to learn everything we can about these messengers from distant stars. Every photon of light we capture from the comet, every spectrum analyzed, every processed image represents a small window into worlds and conditions that we will probably never visit directly as a species.
Friends, there is something profoundly human about this situation. Here we are, a curious species trapped on a small planet, looking upward as a fragment of matter formed around a distant star passes by. We cannot touch it, we cannot visit it, we can only observe it and wonder. Does it not remind you of those childhood nights when you looked at the stars and wondered what was up there? That childlike curiosity is still alive in each of us. Do you still feel it?
The history of cometary observation extends back in time to the very dawn of human civilization. Ancient records from multiple cultures document the appearance of these bright objects in the night sky, generally interpreted as portents of significant events to come. The Chinese kept meticulous records of comets more than 2,000 years ago. The Babylonians included them in their astronomical tablets. The Greeks debated their fundamental nature. For centuries, humanity lacked the knowledge necessary to understand what these celestial visitors really were. Interpretations varied from atmospheric exhalations to purely optical phenomena, passing through supernatural explanations that reflected the religious and philosophical beliefs of each era and culture. The gradual advance of astronomical knowledge, particularly from the 17th century with the scientific revolution, driven by figures such as Galileo, Kepler, and Newton, began to reveal the true nature of comets. It was understood that they were real physical objects, following orbits determined by the same gravitational laws that governed the movement of the planets. Edmund Halley, the English astronomer whose name the most famous periodic comet bears, demonstrated in the 18th century that at least some comets returned periodically, following elongated elliptical orbits that took them from the outermost regions of the solar system to the vicinity of the Sun. His successful prediction of the return of the comet that now bears his name represented a spectacular triumph of the scientific method. Throughout the 19th and 20th centuries, knowledge about comets expanded enormously. Spectroscopes revealed their chemical composition. Space missions, beginning with the flybys of Halley's comet in 1986, provided direct images of cometary nuclei. The European Space Agency's Rosetta mission even managed to land a landing module on the surface of a comet in the year 2014. But all those advances referred to comets from our own solar system. Objects born in the Oort cloud or the Kuiper belt, formed from the same primordial material that gave rise to the Sun and planets billions of years ago. Interstellar visitors represent something completely different. Samples from other star systems, fragments of worlds that we will never know in any other way.
Can you imagine, friends, a future where we receive interstellar visitors with the same regularity with which we now observe eclipses or meteor showers? Each one would be a messenger from a different world, a cosmic letter from an unknown sender. What stories will those future visitors tell us? What secrets will they reveal about the galaxy we share but are only beginning to know?
The universe continues to reveal itself before our astonished eyes, fragment by fragment, mystery by mystery. Each discovery answers some questions, but invariably generates new ones. Each advance in our knowledge briefly illuminates a small portion of the cosmic immensity, only to reveal vast regions of unexplored darkness that extend beyond. 3i Atlas will not solve all the mysteries of the universe. It will not tell us if we are alone in the cosmos, nor will it reveal the ultimate secrets of existence. But it is providing us with something valuable, a window into the unknown, an opportunity to learn something new about the distant places from which it comes. A reminder that the universe is larger and stranger than our limited minds can fully conceive. Astronomers will continue observing, measuring, analyzing. Theorists will continue proposing explanations, debating interpretations, refining models. Communicators will share the findings with the general public, translating technical language into understandable terms for those of us who do not dedicate our professional lives to the study of the cosmos. And all of us, scientists and citizens alike, will continue looking upward on clear nights, wondering what is truly out there in the infinite vastness that surrounds us. It is a question as old as humanity itself, and it will probably remain without a complete answer as long as our species exists. But perhaps the complete answer is not what matters. Perhaps what really matters is the very act of asking, that tireless curiosity that drives us to explore, to investigate, to try to understand. It is what took us from caves to cities, from bonfires to particle accelerators, from cave paintings to space telescopes. 3i Atlas is just the latest chapter of a story that began billions of years ago, when the first stars lit their light in a young and dark universe. It is a chapter that continues to be written at this very moment, while telescopes point toward the sky and scientists analyze fresh data. And it is a chapter that will continue to develop long after all of us have departed. Future generations will look toward the stars with new eyes and technologies we can barely imagine. They will wonder the same things we wonder, marveling at the same mysteries that keep us awake at night. And perhaps, when they read about the interstellar visitors we detected in our era, they will feel a connection with us, similar to the one we feel with those first observers who looked upward millennia ago and wondered what those lights in the sky were.
My friends, we have reached the end of this journey we have shared tonight, but before I say goodbye, I want to ask you something from the heart. If this story made you think even a little, if it made you look at the sky with renewed eyes, if it reminded you of that spark of wonder we all carry inside, I sincerely invite you to subscribe to this channel. There are many more stories like this waiting to be told, and I would love for you to leave me a comment telling me what part of this story reminded you of something from your own life. Perhaps it was a childhood night looking at the stars with your parents. Perhaps it was a trip that took you far from home. Perhaps it was simply that feeling of smallness and wonder before the immensity of the universe. Tell me, share it, because those personal connections are what make these stories take on true meaning. Until next time, dear listeners, and always remember to look upward.